Can everyone hear me well? I think Zoom kicked me out for a minute out of the meeting. Okay, I think we should start. And again, I'll just remind you guys, if at least some of you can turn on your camera, that would be very helpful to see how well I'm doing on the speed and your reactions and everything. Okay. Okay, so let's start. So we're in week 5 right now, just before the reading week. So what are we gonna cover today? So as you remember, in the last lecture, I spent a lot of time on essentially flip-flops, right? Okay, and I hope you learn it quite a bit, and you learn a lot about how to build those primitive pieces to build the memory, right? So the flip-flops is something we're going to use a lot today, and you're going to see how we go from this primitive building blocks that stores 1 bit to pretty much everything you use in your modern computers. So anything that would build would become a basic block of the processors, essentially, right? So after today, you should be better understand things like registers, right? So if you've heard before that computers had memory and registers, today you're going to understand way better how they operate, right? So we're going to learn a lot today about finite state machines and how to build other circuits, more complicated circuits from flip-flops, okay? So this is planned for today. Let's go and check what to do. So as I remind you, we learned last time how to build flip-flops. So we learned about latches. From latches, we built flip-flops. And now our next step is how we can build things out of those building blocks. So essentially, now that we know about flip-flop operation, we know how to make them stable. We learn about all these different, stuff like D flip-flops, T flip-flops, and all these other different things with different characteristics, right? The question is like how we can use them in circuit design and trying to, cut the part of the black magic where it's not clear how we're mathematically doing it, try to make it more systematic. So there's an algorithm for everything we do. And we obviously want to answer a question is that we spend so much time on flip-flops and all these other prior methods. Is it used finally in something real? The answer is obviously going to be yes, but I want you to see how it's building important things. So today you're going to see how some real part of the instructions that you execute with your favorite programming language actually implemented. So essentially the goal is we can show you how you can do something really cool, because saving 0 and 1 doesn't make you that exciting, right? But building something more real that would hopefully would make you more excited and you understand the necessity to understand flip-flops. Okay, something that I announced multiple times and hopefully you're going to learn today well is how to build registers, right? I hope a lot of you've heard about the existence of registers, right? You know that they are there. You probably never thought about how to design them carefully, right? But essentially the easiest way to think about registers, this is something we have for storing values, right? We want to store the values, load and store back, and that's the most active part of our storage. We also had caches, we have memory that this is much slower. The registers is the most active part. And for that reason, it needs to be the fastest, right? And registers are actually quite expensive. Okay, so how can we build something that would be register-like using what we already have, flip-flops? So the key idea, and I'm not going to go over that in details, we're gradually going to build it, but the idea is that flip-flops are designed the way that they can be nicely chained. Remember how we chained adders, right? From a single bit adder, we essentially were able to scale and build any size of adder we want, right? We just scale them nicely, right? And they all just produce the carry bit. It's more or less the same idea applies here. Flip-flops, like for example, D flip-flops can be a building block to store a multi-bit value, such as a 16-bit integer. And this is one example. So you're gonna just connect 16 of those. All of them connect through the same clock. We do clock negated, so it's gonna, go up when the clock goes up, right? And that's essentially the very basic idea. So then the data can be shifted into this register 1 bit at a time over 16 clock cycles. So essentially, the best way to think about it is, remember before when I talk about flip-flops, I was making this analogy as if you're having a pipe, right? And there are two gates, right? You have two closed, and then you open one gate, a little bit of water goes through the pipe, but the second gate still close it. Then I close the first gate and I open the second gate, and the water goes through, right? Just a small chunk, right? That's what I want. So here you do the same type of trick, but just instead of having two gates, right? 2D flip-flops, I had 16 of those, right? So essentially it's called shifting register because the value propagates one cycle at a time, right? It's not just that water goes through all of them right away, it just goes one cycle at a time. So it has its advantages and disadvantages. So it is relatively simple to implement, but remember, it would take 16 clock cycles to the value to propagate. So if I want to store something with this, it's 16 processor cycles. So it's not super fast, right? That's the problem. Okay, so what can we do instead of the shift register? And by the way, shift register might be still useful. It just depends on the context. The load register. So remember, it's just storing is not the only goal we had. We want to be able to load values. So one can also load a register value all at once by feeding signals into each flip-flop, right? So for example, here I'm showing a so-called 4-bit load register. So you see here, those are your usual D flip-flops that we learned in the previous class, and all have an independent input signal, right? So essentially, in one clock pulse, we can essentially store, 4 bits independently here, right? They all have separate inputs. So the strength here, how we cut the latency, is parallelism. So we can actually manipulate them all in parallel. This is a so-called load registers. So this looks cool, but I want to be able to control when things goes in and out the register. So for that, I added a special piece to my D flip-flop that's called D flip-flop with enable. It's relatively simple. Essentially, this part, you see, is like your usual flip-flop. There is no big difference here. It's positive edge triggered. The cloud, as you see, negated here. So essentially, when it goes up, that goes up. What is the difference? The difference is this small piece. How this enable works, let me explain you. It's relatively simple. So essentially, it does two things. So when enable is on, right, then I go through this signal because this is positive and this is negative. So this part doesn't matter. So I got positive and the D. And then this is true. It goes through, this is not. So essentially, this true value here goes through the, OR gate, it becomes 1 and goes in. So essentially what happens is when enable is on, it operates exactly as a regular flip-flop. No difference. It just takes the input D, it puts it in the in input, right? So when enable is on, it has the value D. So what's the feature about enable signal here? Well, what it does is because it uses the output Q out of here and do an AND with negation of an input. So when enable is 0, then this is active, this is not active. And then essentially, then it maintains the old value Q. So what the hell is doing? So essentially, this is really a controllable flip-flop, right? Whenever I say, enable the value, it works as a store, right? So it stores the value D that you give it. If not, it maintains the old value. Remember, when I want to use registers, I really want not only store value, but I also want to maintain the old values I stored, right? So this is what this D flop with enable does. Okay, I have a couple of questions. What is D2? D2 is just a definition not to confuse D. It's really essentially, it's either D or Q, depending on which path it takes. We just, on the circuit, we need to redefine it, right? Think about this as just a different naming, right? Yeah. So Sam asks, so when enable the clock doesn't doesn't make it forget, right? Exactly. So essentially, we don't want to just read and write. We want to maintain the old value, because that's how you want your registers to work, right? When you want to be available super fast to you. You want to place the value, new value to it, that, and then you want to remember that value. That's what this D flip-flop with enable does. Okay. Okay, I hope I answered the questions. Let's continue. Okay. So this is D flip-flop with enable on, yes, and just for everyone remember, so the difference here, it has this EN in the middle, right? So I hope everyone gets it. It's not a fancy complication here. It just, it either operates as before when enable is 1, or when 0 just maintains the old value. We keep going to build in the register. Okay, so now when we have this nice D flip with enable, we can use it to build an efficient load register implementations. So implementing the register with this special D flip-flops will now maintain the values if register in this register until overwritten by setting EN to a new value. So essentially, you see a clock signal, and you had a new bit, right, that sent called write. And when write is sent to be overwrite, right, and then that all will take the input and use it. So as you can see, this is now we get a new bit, like we had a clock bit and we had a write bit. So this is essentially how the reads are different from writes, right? If you ever look at the assembly language and thought about like how things implement in the computer, at the end of the day, memory is manipulated by just load and stores. There's nothing else. Computer doesn't understand anything else from the, intermediate representation perspective. So it only sees this type of instructions. So that's how they're different. Some have this write bit set, and that enables the change, right? So someone is asking, can we just control clock to maintain the value? And another question, so when write is high, the D flip-flops accepts the new D inputs, right? So whatever Terry said is correct. Yeah, when write is high, the D flip-flop accepts the new inputs, right? Otherwise, it doesn't. So can we use the clock itself to do it? Well, the problem, sorry if I mispronounce your name, Zhenyu. So the problem, if I do that, I lose the control when I want to read versus when I want to write, right? So it's not that the clock, like I don't want just, before when we're building flip-flops, we were building basic block, it was changing value in and out depending on what I see as an input. But the thing is, I don't know whether I want to read or write, right? So I need to distinguish these two states. When I want to read, I just want to get the value out of it. And I don't want to read every pulse or every cycle, right? I only want to read when I need this register. So I need to tell it. There is no enough information without this write signal to know when I want to update the values versus when I want to just read the value. Okay, you see the difference, right? In the previous design, you can only do one thing. You can either design one flip-flop that would write the value or read the value. It cannot distinguish. Okay, yeah, so it's just no information. We build flip-flops that do either one or another or invert, like T flip-flops that invert the value, but we need a smarter flip-flop that has this ability to read when needed and to write when needed, and that we just did, right? Okay, I hope everyone got it. Yeah, I apologize if I go too slow for some people that got it quickly, but I want to make sure everyone understands it. Okay. So I don't want to go, too fast on this material. Okay, so essentially in computer architecture that hopefully some of you will take as a course one day, because that's something I do my research on for many years, so I'm definitely close to my heart. So registers are really the building blocks of the CPU most local storage. They used for many, many years from the first processors, essentially. They are the lowest level of so-called memory hierarchy. I know you didn't learn about memory hierarchy too much, but the way to think about it, there is a core where you execute instructions, and we're going to learn how it works in the future lectures. I've just given you a high-level idea. Then there are registers. Registers, the best way to think about it, it's something I have in my pocket, right? Like it's like I had a note in my pocket, I just move it, that's my register. I want to compute something, have it right away. Then there is a cache. The best way to think about cache, it's something that I don't have in my hands, but it might be on my shelf, right? It's the book on my shelf. Then there is RAM. The best way to think about RAM, it's not on my shelf, but it might be in my local storage. So I had too many books, it doesn't fit into my local, bookshelf. I put them in some storage. And the hard disk is even further away. The best way to think about hard disk is like have everything you need, but that might be not fit into your apartment. So that's like a local library, right? So this is the way to think about organization of the memory. Essentially, everything had different capacity, right? But the speed is faster with the smaller capacity. So that the smaller capacity is like, you only had few registers, maybe 100. Then cache, you have several megabytes. RAM, you had gigabytes. Hard disk, you can have terabytes, right? But they are proportionally slower as well, right? So the memory hierarchy is built to provide a good trade-off. So essentially, the registers we're building is really the most fastest and the most local storage we ever going to see. They are the memory units that the CPU directly interact with. Pretty much any computational units you know right now, your mobile phone processors, small IoT devices, sensors on your refrigerator, they all have this type of memory. The registers are the critical for any computation. You might not need cache. You may even survive sometimes without RAM, but registers are critical. You can't really build too much without registers. Okay. So we talk about registers and how we build them. Sorry, there's a question here. Register is between CPU's core and cache, CPU's calculation units. Quintan, I think it's not even between. So registers are literally placed in the core itself because they need to operate at the speed of your compute units. We're going to talk a lot about, in the next class, we're going to talk about LUs. Remember, I showed you a few classes before, I show you how to build adders, right? I show you how you build subtractors, right? But at the end of the day, you want like a universal compute unit that does different instructions. So that's called ALU, arithmetic logical units. We're going to talk about this in the next class. So they're at the core, really, that's what the core is. It executes those instructions using the registers that we are defining in this class, and they manipulate it by some control logic. We're also going to learn about that as well. But they're not even away. Like cache is, 3-4 cycles away. And cycles is, so you understand what cycle means? It's the frequency. So whenever you buy a new fancy computer, it says 4 gigahertz fancy Intel processors, right? That's a frequency. So 1 cycles really matches that frequency, right? So to compute what it really means, you take 1 over 4 gigahertz, right? And you get some fractions of a nanosecond. That's how long your single cycle takes, okay? So caches is like 3-4 cycles away. And registers operate at the same frequency, right? Because they are parameters. When we're going to learn assembly, it will be more clear how exactly they manipulate, okay? Now we're still trying to build those registers. So another cool thing we can build with flip-flops, you probably wouldn't think about, I personally didn't think about when I learned this material, you can build counters. So let's see how that works. So counters. So remember we learned another flip-flop that's called the T flip-flop, or the ones that pretty much similar to D flop, it's just it inverts its value when the T is high. So it has an inversion feature. Otherwise, it's pretty much the same for the purpose of our operation. So what happens if a series of T flip-flops are connected together in a sequence? You see, everything we built is built, it's like an architecture, in a real, not in computer architecture, but in real architecture. We build bricks and we build walls, walls builds, rooms, rooms build the building, right? This is the way we design everything here. So T flip-flops were not defined just, for the sake of fun. They actually are interesting. So you can connect them in chain and can potentially, even more interesting, you connect the output of the flip-flop to the clock input of the next one. So let me show what I mean by that. So imagine that there is essentially this circuit that we have. So we have all these guys here, 4 independent flip-flops. And what we do, we connect their NOT Q output as the input of the next one. So essentially what this thing will gonna do is essentially is gonna try and if you actually carefully look what it does, is going to try to do a counting, right? So although that's not a good design, I will explain in the few next slide, but conceptually what the circuit's going to do is going to count. So it's going to start. So I guess before showing how it operates, let me actually show you, as it usually was one of my favorite examples, if you would demonstrate how the problem happens on humans, but that would require 4 volunteers in the lecture room where they can tap shoulders of each other and you would see the problem. So here you would have to use your imagination today. So, so let me show this mental experiment to you. So we're gonna demonstrate a synchrony problem with the so-called human computer. So instead of T flip-flops, we would have 4 volunteers normally, right? What we would do, each of them given a very simple task. So essentially the Q0 guy would receive a clock signal. So someone's gonna be sitting as an input telling them on, off, on, off. That's your toggle signal, right? So, and so when they see, when you get that, you essentially, Q0 essentially toggles when receive a clock signal. So you get someone tap them on the shoulder to say, you're on now, right? Then the other guys sit around and the way they operate. So then Q1, the next guy, it receives a tap on the shoulder when Q0 goes from 1 to 0. So when you go from high to low, right? That's when essentially Q1 also get a tap. And then Q2 only taps when Q1 flips, and Q3 toggles when Q goes down, right? And then the audience has to kind of try to understand what the number is encoded right now in 4-bit number, right? And very soon you understand that these guys have different reaction to the events, and you might have a synchrony in the situation. You're going to read not what was supposed to be there. So let me show this on the timing diagram. So this is our clock, right? This is the pulses. This is a tap on the shoulder, right? So the clock doesn't go into each of them. You see, the clock goes only in the first flip-flop, in the Q0. So what Q0 is going to do, let's see. So what it's going to do, remember, this is a T flip-flop, right? So it's a positive trigger, so it's going to go up, right? And then on the next things, it's going to, go down, right? So it's so essentially that's the operation of T flip-flop. So okay, so then let's look at what the next one. That's where the interesting stuff starts. Let's look at Q1. So Q1 monitors when these guys changes, not when the clock changes, when these guys changes. These guys changes, as you can see, way rare, right? It changes essentially, so that's where it goes from high to low, right? From 1 to 0, and that's what the T flip-flop detects. So when you go as an input, because that's its replacement for the clock, right? Its input is now the not Q output from here. So essentially it's gonna, when you go from 1 to 0, because we take not Q, so we're not looking when you go from 0 to 1, we look when you go from 1 to 0, then you only go up when this goes down, right? And then it goes at the low, then it goes up, then it goes high, and then it goes down. But you only trigger it when you go down, right? That's how the T flip-flop is built. Remember, that's the operation of the T flip-flop. So essentially, it only reacts when its input goes from 1 to 0. So essentially, Q1 are only going to go to 0 not every cycle, right? But every 2 cycles, right? So so this goes up and down every cycle. This goes on every 2 cycles. That seems interesting, right? What's going to happen with Q2? So the Q2 is going to depend on Q1. So it's going to flip even more rare because it's going to expect when the Q1, the input into Q2 is going to flip, right? So it's going to flip only half of the time, right? So that's going to be 4 cycles. And not surprising, Q3 is only going to go up when this event happens, when the Q2 goes down from high to low. So seems to be I explained it, but why the hell is useful? Like why to explain it? Well, thinking about using this for binary encoding, right? So essentially Q0 is like 0, 1, 0, 1, 0, 1, 0, 1. It's like encoding your low order bit, right? So you're like, if you had a binary number, it's the rightmost bit. Then there is the second one, Q1, that essentially represent their second bit, and this represent the third bit, and then this represent the fourth bit. So essentially, if you, again, use your imagination, look this way, right down. So these, all zeros, 001, 0010, 0011, 011, doesn't remind you something? We just encoded all values, all the binary 4-bit values, right? So essentially, and they all go one by one. So essentially, this T flip-flop just increase the value. Sorry, there is a question. Can we understand it as Qn goes up when meet Qn's down edge? Yes, that's correct. That's pretty much what their T flip-flop does. Okay. Anyway, so essentially this relatively simple mechanism not only allows us to build memory, it actually allows us to build counter. Like really, we just build a counter. Yeah, so there's a correction here. It's if it takes not Qn minus 1 as an input, so that's why it goes not from when it goes up, but when it goes down. Yeah. Okay, so this is what we built, and that's extremely cheap. But the main problem with this is it's asynchronous. So their flipping is not synchronized, so you might get into a situation where something flipped too early and the others didn't flip yet. And that's what the human example is supposed to show. I guess I would have to take 4 of my graduate students and write, video record the example, maybe with our TAs on how that works. But essentially the natural and the problem is that if things flip in the particular order, it's great, but it might flip not at the exact time. So it might happen that 2 things want to flip at the same time, and 1 bit flips and the other one not yet. So you get some weird intermediate step. For example, here you kind of, when things flip, you want, like, for example, here just 1 bit flips, but in some cases there might be more bit flips. So that might create a problem. Yeah. Like, for example, here you see these 2 bits are flipped and this guy is flipped, right? The 3-bit flips between these 2 states. The problem is when the flipping happens, I don't have control over its timing. So it might be this flipped, but this didn't flip yet. So I get this state temporarily, and that can confuse us. Like it means it's not synchronized, right? So because there's no timer that controls them. So essentially what we want to fix this counter to have, synchrony in it. So, and the way we do it, we add a separate additional, write signal that essentially makes sure that flipping happens in sequence, right? You cannot flip. I'll explain this in a second, right? So this is a synchronous counter. So the only thing I did here, you see, I add this separate AND block, right? So before, I was just taking this signal as an input, right? But right now, you see, I took a clock in here and the input is coming from here. So in this case, I don't allow essentially the value to propagate until this thing goes through, right? So it only activated when this thing is changed, right? So it only toggle when the lower bit is 1 and it's toggling to 0. So it generates essentially a carry bit, all right? So this way, I can't have a situation when my higher order bit flip and the lower order bit didn't flip yet. They always flip like from lower bit. Like if you would do it systematically and you add +1, right, to something like say 0, 1, 1, 1, you start to flip 1, 0 to 1, 1, 1 to 0, another 1 to 0, another 1 to 0, and then 1 carry that would propagate to the next bit. So it's the same here. You would do them in a linear sequence. You avoid parallelism. It's an interesting thing how in circuits, you sometimes fight this parallelism, inherent synchrony, while when you're gonna learn more advanced programming courses where you're gonna be a lot of effort you're gonna spend on parallelizing stuff, right? To making sequential things being very parallel. While circuits are very inherently parallel, they don't have, if you don't have control logic them, they all simultaneously operate. And as a humans, you're going to see we're not actually very good at debugging and understanding the programs that are so parallel, right? Even though our brain works in a very parallel fashion, to the best of our understanding, when we reason about programs, we way more frequently prefer sequential code. Okay, so we can keep building on this counter. We can do counter with a parallel load. So essentially, we can get an extra, max here, right? This is just a little max within 2 input that you see we had now a load signal and a write signal, and that would allow us to build a counter that we can also load the value from in parallel, not just counting, because whatever I designed before was just counting. I can't really read through it, right? So it was not, it was a thing in itself, right? It was counting something, but nobody knows what it's counting, right? So this way, I can have a signal that writes values into this. This is a 2-bit counter, and I can also parallelly load it. And the way it's built, it has a max, right? Depending on the input from a load, it operates either as a read or as a write, right? Okay, so essentially this load signal might disable the write operation and just then read the value. So usually those counters are often implemented with a parallel load and clear inputs. And you can send the counter to whatever you need with the write, and load can, update it. So whenever, if you use hopefully C, C++, whenever you have something like ++, now you can think about how this instruction can be efficiently implemented, right, in real logic. Okay, so essentially when load is high, it sets states to R0 and at 1, right? So, that essentially allows you to load the values. Yeah, so load forces the specific behavior, right? So they forces you to essentially to generate the output, right? So you can read it, while it actually load the values into it. Yeah. Okay, so that was just an example. We are not going to actually, grill you too much on counters, but you need to understand the basics of it and how we build from that. So that was just more like an example of cool stuff we can build with flip-flops, right? So you can see that the main usage, obviously, we build them to get registers. That's a key thing. But as a nice side effect, we can also build counters, right? Because if you think about counter, we always think about counter as being just an arithmetic instruction. It does ++. But remember, to do ++, right, it needs to know the previous value. So it has to have memory, right? So you can have that memory separated in a different register, and you do add +1. But that's an overkill, right? So we're showing there's much better design to design counters like that. Okay, now time to talk about state machines. That doesn't have to do anything with our neighbor to the south. This is something that comes from math. Essentially, we're going to talk about state machines. And the reason why we need yet another level of complexity is because we want to understand how we're going to build generic circuits to store value using flip-flops. Right now, I was more like a magician. I'm showing like, oh my God, let's do this circuit, connect this, do this sequentially, do this way. So I was doing this more like an examples of how the cool things can be done, and they were relatively simple. But obviously, the more sophisticated circuits we build, we need the right machinery. So we will try to a certain level answer the questions, how we can design the circuits with flip-flops, and what could you design with this circuit? So what would be efficient with them? Okay. So essentially, sequential circuits are the basis of memory that I said multiple times for you. Hopefully, if you remember something for this class, you would remember that. So it's essentially sequential circuits are required to build any form of memory right now. So it helps with instruction processing, any other operation that requires the circuits to remember any past values. That is pretty much almost all instructions are like that, if not, well, not everything, obviously, but there are a lot of instructions are like that you're going to execute. So essentially, all of them would require sequential circuits. These past data values are also called the states of the circuit, right? And we need a way to describe the relation between the current state and the next state, right? Essentially, our goal is to figure out how, by looking at this circuit, I can explain how it operates, right? How it goes from this previous old state into the new state, right? And we can do this using combinatorial circuits. Okay, so let's look at the very simple example of the counters. With counters, each state in the current number is stored in the counter. Let's say we had a 3-bit counter, right? So how many values we have if we had 3 bits, right? All different values in this counter. How many we can store? So anyone who can count well or think quick? Just post it in the chat. Yeah, exactly. It's just 8, right? 2 power 3. So essentially that's what we have here. So this is 8 states using 3 bits, right? I hope everyone understands. This is a 3-bit counter. Then on each clock tick, the circuit transitions from one state into another. That another state might be the same or different. So how we draw that in a finite state machines? So bear with me here if it looks too complicated. So for example, this 0, 0, 0. If the input is 0, so that it's not enabled, right? There's no enable of the change of the counter. You just stay in the same state. This is what the arrow shows. This arrow shows if I was in the state 0, 0, and I had 0 as an input, nothing changes, right? That's very simple. But then if my input is 1, I go from state 0, 0, 0 into state 0, 0, 1, right? That's a transition, right? So depending on the input, which is 0 or 1 into this, part of the circuit, I essentially, so this is my states, my old state, and this is a transitions, right, from the states. And it's very simple circuits. Essentially, everything is circularly repeated. So 0, 0, 1, 1, if I had a 0 input, I stays the same infinitely here until I get 1, then I go into 0, 0, 1, 0, and so on, and so on, and so on, and so on. Okay, so this is how we build for this circuit, this transition diagram. Then one thing to think about it, has nothing to do with binary, right? There's, finite state machines in which we're going to work with, they had nothing to do with binary. So there can be any state. You can call this number 0, 1, 2, 3, all the way to 7, right? And that's your state. So you can call the states the way you want, right? So each state doesn't need to correspond to any binary number. They're just different states, right? That's what's important, because that's more general than, like the finite state machines is a general concept that you probably learn in some of the math courses. If not, you're going to learn a little bit in today's class. Okay, how are we going to build the state tables? So this is very similar in a sense to truth table, right? So essentially we had a state and we had an input, right? So I had state 0. If I write 0, nothing changes. If I had 0 and I write 1, then it becomes 1. And the same here. If my state was 1 and there is a 0 here, it stays at 1. If it's 1 and transitions, it's all the way the same going up until 7 goes back to 0, right? So essentially state tables help to illustrate how the states of the circuits change with various input values, similar to the truth table, right? So transitions are understood to take place on the clock ticks. There are some complications with these transitions, but for simplicity, we assume that they happen on the clock ticks. How are we going to do the next step? So how are we going to transition from here into building a flip-flop? Like, because that's one of the goals. We want to take a problem, convert it into finite state machine, and then finite state machine, think about it, this is an abstract object. It's a mathematical object, right? It doesn't exist on anything physical. The physical thing exists. It's the flip-flops. It's the transistors, right? So we want to convert this mathematical object, this mathematical abstraction, into something real, right? So the state table help us to do this. So essentially we use, so we remember this was a 3-bit value. So hint from me, for a 3-bit value counter, you need 3 flip-flops, right? We already learned that before. So essentially, I would need 3 states, and that's what I'm going to use flip-flops as F1, F2, F3, and they're both inputs and outputs, right? Because that's a cool thing about flip-flops. The way we use them, we can use the inputs, outputs as the inputs. So essentially, this is the way we re-encode everything. So it's just, this is a binary encoding for everything. So that's going to be 0, 0, 0, 1, and all of that. Okay, so flip-flops where they're both input and output of the circuits. which brings us to a formal definitions of the finite state machines. So essentially, before I kind of bring up you to the need of this concept, right now I'm going to formally mathematically define you what it is, more or less formally. From your theory courses, you probably might remember, or I don't know, depending on which courses you took before, but a finite state machine is an abstract model that captures the operation of a sequential circuit. So a finite state machine in general defined by a finite set of states. That's why it's finite state machines, right? And that's why it has state in it. And it also has a finite set of transitions between states triggered by inputs to the state machine, right? So the state machine gets those inputs or transitions that change it. And output values are associated with this each state or each transition depending on the machine, right? Start and end states of the machines might be added as an starting position and end position. But essentially that's what it is. There are states, there are transitions that pretty much explains the whole logic of the circuit. Okay, so how are we going to design something using this? Very, very roughly. So essentially for combinatorial circuits, when we design, we had a desired behavior, right? That's what we look at. We have a truth table, then we build logic expression, then we build circuit. This is just, I'm reminding you how we build things. And you've seen this before, like we play with K-maps, that's how we build things. On the sequential circuits, essentially we have something very similar. We look at their desired behavior, but that behavior is much cooler because it has all these fancy transitions, right? Input matters. Before, when we had combinatorial circuits, all my inputs fully define my outputs. Remember, it's very simple to build, but it's quite boring. It doesn't have memory. But the sequential circuits does have it. So instead of truth table, what we get, we're going to get a finite state machine, right? That's what we get. And then we're going to use finite state machines. We're going to try to convert it into, into the state table, as I just showed you informally. And that we're going to convert into flip-flops. We're not going to do it in an optimal manner. We don't have time in this class for that, but we're going to show you some way to map it. And I'm going to give you some reference where to read on the more efficient methods. Okay, what's the best way to think about it? Let's use our Elmo again. I hope a lot of you've seen it before, and I posted a video before, but I just remember how it works, right? So this toy reacts differently every time we squeeze it. And despite it's very simple, it's actually not a combinatorial logic inside of it. It's actually a sequential circuit inside of it. The first time I squeeze it, it says, ha, 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 that tickles, right? That's the first reaction. The second time I press, it's not repeat the same thing. That's what it makes it exciting for kids, right? It starts to say something different, says, ha, 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 oh boy, right? That's the next thing. You press, the third one is it goes crazy, it just laughs, and if you press another time, it goes to the first state, right? So the question to ask, if I want to build tickle circuits, what are my inputs, right? So what are the inputs? And what are the different states of this machine, right? So how would you build that circuit? Because like jokes aside, there is a circuit inside of this thing, right? A very primitive, but it is a circuit. And how do you change from one state into another? So how would you design something like that? Okay, so we define three states, one called tickles, one calls oh boy, and one calls go crazy. So these are the three states of the Elmo operation. It has this initial stage where we just, talk, tickle. We just bought Elmo, sorry, and we never touch it, right? That's the initial state. It only exists at that stage and never after. So after that you play, it always remember whatever was the previous state. Okay. Then the operation you have is squeezing, right? That's a transition. So you squeeze, it goes tickles. You squeeze again, it goes to oh boy. You squeeze again and go crazy. And then it goes to tickle, right? There's no lack of, it just goes in circle afterwards, right? That's what the circuit does. Okay. Another very familiar example of the sequential circuit that you should be familiar, I hope, is called traffic light. So it has three states, red, yellow, and green. So how that does operate? Well, there is a change flag that actually goes with timer. Timer might not be equal for green, red, and yellow, but there is a timer. And essentially the timer said there is a change, time for change. And you go from yellow to red, from red to green, from green to yellow. That's a very simple traffic light operation. Okay. Obviously, if there is no change, then you get just circle there. You just stay in the same state. Okay. So you see a lot of things you've seen in real life already had this, circuits built in them. Okay. So now a little bit more formally. So the way we're going to define a finite state machines is first we're going to draw a state diagram. And here I'm showing something more complicated. Those diagrams use in math and other things for a long time. For example, when you try to translate things and figure out how to pronounce certain words in a new language, this is a very good ways to describe sequential operation or sequential circuits. So first, step one, you draw state diagram. Then you derive a state table from state diagram, right? So that's what we already built before for very simple cases. Then you take the state diagram and you assign flip-flop configuration for each state. So each state is modeled with one particular flip-flop, right? And then you redraw the state table with flip-flop values. So you replace all this, go crazy and tickles with the actual flip-flops, right? And then you derive a combinatorial circuit for output and for each flip-flop input. So there might be some manipulation with the input outputs to get the right results at the end, right? But that's a combinatorial circuit. It's so simple, and that's it. So that's the last step where you just like you already had all the parts of your output. You just need to merge it into an AND or some simple combination of the output. Okay, that's pretty much what your finite state machine design is and how it can you help to build the actual circuits. Okay, one example is a sequence recognizer. It recognizes a sequence of input values and raises signal if the input has been seen already. So one example of that is 3 high values in a row. So for example, say if I have seen 3 ones, signal me, right? So I want to recognize the signals. Where it's important? Well, all forms of encoding, like when I see different encodings for different signals and I want to raise a flag for one particular one, that's a sequence recognizer. So you want to detect that the input has been high for 3 rising clock edges consecutively, and you assume a single input X and a single output Z. Okay. So the first questions we need to ask are, what are the states? So the questions for you, what would be the states for this machine? If I want to work to build something that could detect 3 high values in a row. So what are the different states I need to observe? You can list some. Like, what do you think those states should be? Okay, I hope I didn't lose you guys. So just think about it. I only care about 3 values. So what should the states be? Start and 1 to 3 is not enough because I essentially need to look at all the different groups. So I need to look at all different combinations. So I think Sam was close to it, but I don't need 2, I need actually 3. So essentially in this case, the states are labeled with 3 most recent input values, right? Because I need to control all of them and all the transitions. So, and transitions between the states are indicated by the values on the transition rows. So this is what I want to build. So reasons why, because I can control even more states, 5, 6, 10, but I don't care about them. The only thing I need is to see this 1, 1, 1, right? So what I care about is how the combinations of 3 last things changes, so I can see how they're going to go into this state, right? So essentially the most straightforward way to build it is to build it essentially having states with 3 bits. So is this clear why I use 3 bits? Because that's the only values I care. Everything else doesn't really matter. So I don't look at longer sequences. I could define something more complicated, but the minimum I need to track. Yes. Yeah, so it's like there are no, it's not, so there are not 3 states here. There would be 8 states. I need to detect that 3 bits in a row are all ones, right? So this is all possibilities here. I might have 0, 0, 0, right? And then if a new 0 comes, what I'm going to get, I'm going to forget this 0, and I'm going to get new 0, 0, 0. But then if a 1 comes as an input, I'm going to forget this 0. I'm going to get 0, 0, and 1, right? That's what happens. That's how I interpret a change in sequence as an input. So if I had an input that sends me 0, 1, 0, 1, 0, 1, right? 0, 0, 0, 1, that's how I interpret those things. And then, for example, if I'm in this state and new 0 arrives, what I'm going to get 0, 1, 0, because I forget this thing. It doesn't matter for me anymore. I need 3 last consecutive ones. And then I bring another 0 at the end of it, right? Append 0 here. And if I had this state and then 1 arrives, I go into 0, 1, 1. Okay? Does it make sense? So this is essentially the state diagram. I think we are at 12 right now, so I want you guys to have a well-deserved break, and I'll see you back at 12:10. Any questions so far? Okay, so see you in 10 minutes. And thanks to everyone who turned on your camera. That was very helpful. Thank you. Okay, I hope you guys have a nice short break. And please, for people who can turn on the cameras, please turn it on back, and we'll continue in a minute. Okay, so let's continue. So we just went through one example, and I show you how we built a state diagram. So just remind everyone, the goal in this example was to essentially detect 3 consecutive high values, which means 1, right? And essentially, because we only care about 3 values, then that's the only thing we remember. Everything else we forget, right? So the way we design things here, as you can see, that I don't track 4 and 5 and more values. I only take the 3 last one because that's the only thing that affects my output. And then I had transition states for each of them. So anyone has any questions on how that works? Please ask questions now. Okay, let's continue. So let's look at state table. So remember, we need to make sure that the state tables leads all the states in the state diagram. So and then it also depends on the input. So essentially, this is a little bit of a complication from a regular truth table, right? You had 8 different states, and there are different inputs. Luckily, the inputs are binary here, just 0 and 1. But this alone gives us 16 different possibilities, right? So I want everyone to understand it, right? For each state, we can have 0, 1, 0, 1, 0, 1, and so on. And the output is the next state, right? So that's our output. Okay. So when we get that, the next step is to get from here to flip-flops. One way to do it is assign flip-flops for storing states. And a single flip-flops can store 2 values, 0 and 1, as we know. So thus we can represent 2 states. So the question is, how many states can be stored with which additional flip-flop? So essentially, 1 flip-flop stores 2 states. 2 flip-flops stores 4 states. 3 flip-flops stores 8 states. The question is, if I had n states, what would be the formula for how many flip-flops I need? So please try to get that. It just would help you to see whether you understand it well or not. Yeah, you need to be careful. Yep, you need ceiling, right? So because nobody said that n is necessarily power of 2. So essentially, 8 flip-flops is to power 2, but essentially n states you would need a ceiling of log 2n flip-flops, right? Remember, as we have seen before, sometimes when we had something not power of 2, we're going to get some states that may be not utilized, right? And we use some undefined states for that. But the bottom line is that's the maximum. So we always had to round. And sometimes it's substantial, right? So for example, if you had, I don't know, 150 states, right? 128 is not enough. 256 seems like an overkill. I had 100 extra states, but that's the only thing I have, right? So it's a ceiling of log 2. So I still need 8 flip-flops in this case. Okay, so how many flip-flops we would need here then? Yes, it's just 3. That's correct. Okay, so how are we going to assign the flip-flops? So in this case, we need to store 8 states. 8 states, as we said, ceiling of log 8 of base 2. So it's just 3. So for now, we assign a flip-flops to each digit of the state machine in the final state machine. So this is, we don't have any better way. So that's a simple thing. We just assign flip-flop for each bit, right, that we need to store. Might not be optimal, but it would work. Right now, the goal is to make something to work. And essentially, then we would map then a state table to the flip-flop values. So essentially, this is, remember, our previous state inputs and next state. And essentially, we just go from these previous states into our flip-flops. So we had F0, F1, F2, F0 for the first bit, F2 for the second, and F2 for the third. And essentially, this is our output, right? This is also the flip-flops. So remember, this is just one way to do it. This is not the only way. This is not even the most efficient way, may not be even a good way, but this is the way that would work in a straightforward fashion right now, okay? There are more optimal way, like remember, similar with K-maps. So it's not fully optimal, it's optimal to a certain point, right? It's only optimal taking certain rules into account, but you can still do some, changes and make a better, formula than K-maps. It's the same story here, okay? So how we're going to design a circuit for something that we just had. So essentially, I had three different outputs, F2, F1, and F0, right? Everyone sees this, right? So I had I had essentially F0, F1, F2, F0, F1 that are the inputs into my flip-flops. Then I had an extra input, En, right? And I had three outputs. That happens to be the inputs into their flip-flops as well. How are we going to do it? We're going to do a corner map for each separate output. So we had F2. We need to compute how F2 is going to operate based on F1. So for your own simplicity, remember I said we essentially convert the sequential circuit representation into something that is very similar to a truth table, right? So it has 4 different inputs, and essentially that's like 2x2 matrix for the kernel maps here. And as you can see here, this is essentially the values that define the behavior of this circuit. So if we just look to the truth table and look at the values there, just simplifying your life so you don't need to go back and forth, but you can check me later on. This is the truth table I'm going to get, and that's essentially the K-maps that I'm going to get there. Well, it's relatively straightforward to apply K-maps to that. So you see there's all these ones that are in the middle that form 4x2 matrix, right? Which gives us a very nice equation at the end. F2 equals F1. So this is the design we need to do for the first output. F2 just equals to F1. So F2 is the next state. F1 is the current state, right? That's essentially what it transitions. Okay, how about F1? If we're going to look at the same table that I showed a few slides ago, and we plot all the zeros and ones, that's what we're going to get, right? We're going to get, 2x4 matrix instead of 4x2. But the good thing about it, we're going to get F1 equals to F0, right? Okay, so again, next states versus current state. And this is what we're going to get for F0. Surprise, surprise, F0 just depends on the input, right? So this is essentially the sequential combinatorial circuits for our sequential circuits. We're almost there, but not fully there yet. So essentially what we got so far, we got the behavior of each individual output for each individual flip-flop. So this is 3 our flip-flops. That's flip-flop F0, flip-flop F1, and F2, right? This is D flip-flops, right? Those are their inputs. They are, positively triggered, so the clock has to be negated. This is the clock, right? So we already figure out what are the outputs they generate us. So resulting circuit is going to look like what I show in this diagram, but I didn't really connect things properly yet. Remember, I said at the end, we need to properly connect the inputs and outputs of each flip-flop. And then we also need to generate the final output, which would be just a combinatorial circuit out of these flip-flops. Combinatorial meaning I'm going to take and do AND or some other manipulation with these outputs, right, based on the logic I need. Okay, this will record the state. So remember what the flip-flops allow us to do, and they record the state of each individual bit, right? At the end, I don't need just record. I want to figure out when all 3 are equal. But that's what I'm going to get essentially here. So essentially, these guys say F2 equals a 1. It means that their output of this guy goes as an input into here, right? That's the connection I need to build between these two. Then from here, I go into here, right? And then input, right? Input goes into F0, right? It might be, as you can imagine, it would be more complicated math. You might have multiple inputs going into F1, F2, and they might be connected with some AND and OR. So then you would get some extra circuits here, right, on these connections. But I specifically pick a simple example so you can track everything, right? You see, if this would be, say, F1 and F0, right? So then I will give you an output from here, an output from here, then I had an AND, right? I connect them through an AND, and then it still goes into there, right? It's still not too bad, right? But this is just even simpler. Okay, you got it, right? What you do. We're almost there. What's missing? So I connect everything. Seems like everything locks, but what's missing? Okay. Yes. So someone says output. So right there, the question is, at the end of the day, I do all this thing to generate an output, right? Right now, this thing computes what I need, but it doesn't generate it anywhere. So what I need to add, we need to get a value z, right? The output, which should have the high value when we have 3 high values in a row. And what that would be the Boolean equation for z. Well, it's essentially F0 and F1 and F2. So these circuits guarantees me that I get sequential 3 equal, right? This thing just tells me I need it to be all ones, right? So it has to be all equal. So this gives me all all the same values, right? So anyway, this is just the output. You just need to AND of all 3, right? So essentially just F0 and F1 and F2. That's what you do, right? I apologize, I simplified here, but like you can either build a 3-input adder, AND, or you can imagine this would consist of 2 ANDs and then another extra AND, right? But this is what logically happens, right? So you connect things intermediately based on the equations you got, and then you generate output based on the value that you need. Now that's pretty much it. So right now I really show you, we took a problem, and in around 10-15 minutes, we were able to come from that into the circuits that had, it's actually a non-trivial thing. It has memory, it can compute, right? So it's essentially, if you would build something that would implement, I don't know, traffic light or an L more or less, right? So this is what the circuit would look like for something like this. Okay, that's roughly in complexity similar to those circuits. Any questions? Okay, sorry. So how one flip-flop stores 2 states if one state consisting of 3 bits like 1, 1, 1. So one flip-flops stores 0 and 1, right? So it stores 1 bit. It doesn't store 2 different states. It stores a bit of a state. And the states is built out of multiple of those bits. So 3 flip-flops, right? It can essentially store 2 power 3 different binary values that represent 8 states. So Z, did I answer your question? And then the second question is, so we'll look at each bit of state and see how each bit is affected by other bits. More or less this, yeah. So it's roughly, so essentially it's the same as in regular truth table, right? You need all inputs, right? You just convert a more complicated finite state machine into the static table, right? And it can be quite large, but essentially it's the mechanism that works. Okay. Any questions here? Okay, let's move on. So something I'm not going to cover too much today, not to overload you, but I just need to tell you that those things exist. So we essentially have something called Moore machine and Mealy machine. This is 2 ways to derive the circuits needed for the output values of the state machines. So essentially the Moore machine is, it uses this main principle where the output of the finite state machines depends solely on the current state, right? And based on some entry actions. and the MIDI machine is more generic. It makes the output of the finite state machine depends on the state and the input, something we tried here. And being in state X can result in different outputs depending on the input that caused that state. So those are the two different types of machines that you can potentially deal with. Okay, one issue, right, that I didn't cover so far, but it is quite non-trivial. I touch upon it a little bit when I talk about a synchrony problem. Again, I reiterate this again and again. Whenever you deal with circuits, with physical devices, they naturally had plenty of parallelism. This parallelism is a bad and a good thing. It's like dealing with electricity, right? It can help you to achieve a lot of things. You misuse it and you can get killed, right? So the same with a synchrony. A lot of parallelism, right? If it's not controlled, it becomes completely asynchronous. Some cases, it's completely fine. So imagine, for example, I need to come up with the sum of all, like each of you generate a value, right? I said the whole class generate a value, and then I say, let me compute a sum of all the values you guys generate, right? This is a classical problem that has a lot of parallelism. And if I need a sum, I can use any order I want. I can, for example, if I'm smart, instead of going to each of you and add up each value one by one, I can tell you form pairs, then form quarters, right? And get a tree adder, right? Like I would let you guys add your numbers and then give me the intermediate sums up. And the cool thing about it, doesn't matter how fast you are, no matter how quick you count and who count faster, at the end, the result is the same because, you know, it's addition is commutative, it's also associative, so all the orders doesn't matter, right? Like it doesn't matter in which order you're gonna add up your numbers, right? And even if you add the same numbers, because they can have intermediate sums, the final result is the same. So you can build a synchronous circuit to do this type of computation or a synchronous computation, and that's not gonna hurt you. Unfortunately, there are a lot of cases where you need certain synchronization. The algorithms are built this way, right? So here, it's no different. And we're going to see where these problems arise very carefully here. So assume we have this state machine here, right, that have 0, 1 state. It has all these other states. So something, it's just a short version of the scheme we've seen before, right? Remember? So this is when we look at 3 sequential ones. This is a recognizer circuit. Remember, we would try to recognize 3 sequential ones. And I'm just for simplicity show you just a piece of this diagram so you can focus on this piece. What the problem is, if recognizer circuit is in state 0, 1, 1 and gets a 0 as an input, it now needs to move to a new state, right? It moves from a state 0, where's the 0, 1, 1. It needs to move to this state, right? From this 0, it wants to transition into 1, 1, 0, right? The problem is that to go from here to here, I need to have 2 toggles. 2 bits needs to flip, right, for this to happen. So mathematically, there's no problem. In math, all these things usually doesn't exist. It's just like I say, well, just flip 2 bits simultaneously, right? That's what I would say, right? And that's how you do it logically. But in your head, you actually had this internal synchronization barriers, right? You're not going to get into undefined state. The problem here, if I had a circuit, it doesn't know in which order thing needs to finish, right? It's a flip-flop, it just flips bits, right? The first and last digits should change at the same time, but there is no such thing unless you implement it as at the same time, right? So there are delays, there's a propagation of signal, things are not going to be activated the same way. In fact, pretty much everything in the computer is discrete in some sense. So what might happen is that if this bit flips first, right? If this bit flips and this one didn't flip yet, out of a sudden I had an intermediate state that looks like 1, 1, 1, right? So I am not supposed to go this direction at all, but I get this transient state where it becomes 1, 1, 1, right? So, and then I go from here to here that also doesn't exist in my table. So you see the problem. It creates a race conditions, right? It depending on which bit flips first, it might or might not create a problem. So for example, if the first flip-flop changes first, the state will change to 1, 1, 1, and the output Z would go high by seeing that. And this is an unexpected behavior. Like I get a transition state here that goes up and generate me. Like imagine I would do this for, for traffic lights. So for a blink of a second, I might get a red that even if I'm supposed to see a red right now, right? And, it can have a catastrophic effect, even that it's a short thing, right? So we don't want an unexpected behavior. It's interesting that not every problem, like not every asynchrony brings up a problem. That's another thing I want you to remember. It's like whenever you're going to learn parallel programming, if you don't learn already, and you're going to lead with different synchronization primitives, like such as locks, semaphores, you're going to see that sometimes you might violate them, but the results are still correct. So not any form of uncontrolled asynchrony leads to a problem, but some might. So if the second flip-flop changes first, so we were planning to go from here to here. If the first goes changes first, the first bit changes first, I go here, and that's a problem. But if I go into 0, 1, 0 and jump here, it's fine because this intermediate state does not cause an unexpected behavior. It doesn't lead to a trigger in the output. So you see, I might jump to the direction I'm not supposed to jump. I might go from here into here, right? But that doesn't cause an unexpected behavior, right? So this direction, even though it's not in the original graph, doesn't cause a trouble, right? So you see the difference. Asynchrony can create issues, and some of them leads to unexpected behavior, those red points, right? Red lines here, and this doesn't, okay? Okay, no more questions. And then we go back here. So you can get this yellow like this or like that, right? Okay, so how are we going to solve these things? So this timing assignment seemed to be a problem. So there are two possible solutions. One thing is essentially add more restrictions. That's how the government likes to operate. If they cannot solve a problem, they just impose some extra restrictions on you, and that solves the problem, right? So that's one solution here as well. So essentially, if we know that 2 simultaneous bit flip causes a problem, well, let's avoid such situation. So let's do some conversions in our truth table or state table, such we never had a pair of bit flips at the same time. So we make that everything flips just one way. You can fairly ask me, oh, it's not always possible. And you would be right, assuming that I'm using the same number of flip-flops. But if I use extra flip-flops, right, then I'm going to get some states, right, extra. So for example, for 3 bits, for 8 states, when I use 3 flip-flops, every state is used. There is no way to get from all zeros to all ones, always flipping just 1 bit. You can try this as an exercise if you want. But if I get an extra flip-flops, then I can define an extra states that are not needed, whatever way I like, 0 or 1, right? And then I can play this game. I can go transitioned in a way that is always flipped just 1 bit. So I can create some extra auxiliary intermediate states that are allowed and generated by those states in a consistent fashion with the output of the starting or the destination state. So you got the idea briefly, right? So even if it might be not always possible if all states are utilized, but if the timing issue is a big deal, and you can see how it can be a big deal, people might add an extra flip-flops and define some extra states to deal with this. If the intermediate states are unused in the state diagram, you can set them output to whatever way you want, and that might help. So you can put them to something that won't create a trouble for you. So it might create essentially somewhat of a race condition, but it doesn't lead to unexpected behavior. That's the thing. Remember, you can lead to the side trails as with these green arrows that I showed before. That doesn't lead to a problem in the output. But that's not for free. You would need to add more flip-flops. So for example, if, for example, state 00 does not have to have a flip-flop value 00, it can be assigned to anything you want. And so the home exercise for you to practice is trying to reassign something in this table, assuming on what the problem really need. Like remember, I assigned all 00s to all zeros just for convenience. but it doesn't have to be all zeros. I can redefine it to whatever is convenient to me. So maybe that would help. Yeah, so just play this game. Okay, another interesting example we want to for you to build, and I'll just explain a little bit on how it can be built, but I want to practice at home a little bit. So that's called mouse clicks. It's very simple. I want you to design a circuit that takes in two signals. A signal P, which is high when the user is pressing a mouse button, right? So you had a traditional mouse and you have a mouse button. And there is, so that's a P, or press. And there is a signal M, which is high when the mouse is moved. So there is a sensor there that would amplify the movement of the mouse, right? So it detects that and would generate the signal M for you, which is move, right? Based on the inputs, indicate whether the user is clicking, double clicking, or dragging the mouse on the screen, right? So those are the states, that's your output, right? You had two inputs and you had those outputs. And essentially, this is something, like I'm helping you to build this transition table so you can build a circuit out of it afterwards. So look at it. So for example, so what are their potential, like the first complication here, obviously we had two inputs, right? Remember before we always deal with one input, right? 0 and 1, right? So essentially I only had two arrows, right? From each state. So when there was one arrow, like if it's 0, I usually stay in the same. If 1, I go somewhere. Here things are a little bit more complicated. So essentially the way we encoded here is the first signal was mapped to 1, and the second one, the first signal for P, for pressing the button, is the first digit in this transition table, and M, the movement, is the second one. For example, let's look at state called, so essentially there is a state called clicked, right? This is where you click the button, right, just now, and then depending on what you do right now, you want to understand whether you stop clicking, right, which means released, right? For example, if it all ones, it means you're dragging an object, right? So you clicked and move, that's called dragging, right? And then there are this neutral state where, you want the click state and then you don't click anymore, right? But you're moving, right? So you can move to a neutral state. So essentially you can go through this diagram and see how it's defined and verify if everything is correct here, right? So it's because I steal this slide from one of the previous, lectures in this course. But I believe here everything is fine when I look at it. So essentially outputs depend on the state, right, only, which is a Moore's machine. And their idea is that part of your exercise at home is to try and build a circuit for the mouse based on these finite state machines. So you see, this is your finite state machines, right? Those are your, essentially inputs, right? Those are states. You see we have how many states here? 5 states. You would need to decide for these 5 states how many flip-flops you would need, right? You're going to first build, a state table, right? How we practice before you're going to have this different state with the names first, and then you're going to, take those inputs and then you generate outputs where we are. And then, so the outputs again, there's also states. And then after that, you would start to convert all these, English words into flip-flops, right? You're going to figure out, hopefully based on the math we did, how many flip-flops you need, right? You're going to use them, and then you're going to try to define a state table, right? And that state table, you're already aware of the problem of asynchrony, so you're going to try to, assign things in the truth table, in the state table, such that we avoid multiple bit flipping at the same time if possible. And then we'll try to get, the final, circuit and just test it, right? So see whether it works or not. You can use Logisim or something like that. Okay, so this is pretty much everything I have. We finished early today, and I don't want to start a new topic on the process architecture. So I'm here to ask any extra questions you might have. And if not, I'll see you on on Friday. One quick update that I forgot to mention about the quiz. I think that the last quiz was a little bit easier for you guys. I felt like we didn't have any major problems, at least based on the personal emails and Piazza, like everything was resolved reasonably well. Obviously, the quiz that will be happening this week depends mostly on the material from last week, but maybe still a few minor questions from this week. And since it's on flip-flops, it's going to be probably more complicated for you. We'll try to keep problems simple, but you also try to revise the material from last week so you don't forget. Because there's a trade-off here. If quiz is mostly based on the last week material, you cover it, but you might forget some of it. If I do it on something fresh, you still remember it, but not prepare well enough. So try to refresh some materials before the quiz. And remember, the main goal is not about grades on the quiz. It doesn't add that much to your grade, but mostly making sure you learn the material as we go through the course. And that would help with your labs as well. Obviously, we're not assigning any labs next week because it's a reading week. So you can catch up on anything you do or just have a break. That's it. I think any questions you guys have? Someone asked, can we have a lecture notes now? So essentially, every time I finish the lecture, I send the lecture notes immediately to TA. They usually publish the notes within a few hours. They just convert it into PDF, so things are usually available very quickly. Okay, yeah, and the videos after they are converted, and by the end of the day, we will also share, so you can revise things I said again. Okay, thank you guys. See you on Friday. Bye.